All right, let's look at 4.7, which is on coordinates and change of basis. So first up, recall what a basis is. A basis of a vector space is a set of linearly independent vectors in that space that span it. So the thing that's special about a basis is every vector in V can be written as a linear combination of the basis vectors. That's because they span V. And they can be done that in exactly one way because they're linearly independent. So I've got two bases here for R2 written, and I want to look at these different points we have. Now, these are points, or we could think of them as vectors, so I'm going to label them. This is going to be V1, this is V2, and this one V3. And if we come over here, I want to just list out the coordinates of these things. V1 is, let's see, -2, 4. V2 is, let's see, that's 5, 5. And V3 is 4, 1. Now, what I'm writing over here are the coordinates, and we think of those as like the normal coordinates of the points, but those are the coordinates with respect to the standard basis. So, what if we wanted to get the coordinates with respect to this basis? Well, what that means is we want to figure out what are the coefficients of this basis. I kind of glossed over this a second ago, but for V1, the coordinates -2, 4, those are the coefficients you would put on these two vectors in order to add them up and get that point V1. So what about for these? Well, we could solve a system to do it, but I wanted to start with an example that's easy enough to just do by hand, or just by looking at it. Now the basis, let's look at T. So we've got the vector 1, 1, which is this guy. Then we've got the vector 0, -1. So it goes over 0 and down 1. So we've got these two vectors here for T. And this might be silly, but the way I think of this is this vector points off this direction, and this one goes down. So it's kind of like, say we wanted to get to to V3. It's kind of like this would be a crane, where you'd have to extend up to, let's see, up to here, like for the crane itself. And then you drop the line down here to get to V3. So if you look at what that would take, it would take 1, 2, 3, 4 of those guys, and then 1, 2, 3 of those. So for V3, what we could say is, V3, its coordinates with respect to T. This is the notation for that. Let's see, we had to multiply that first vector by 4 and the second one by 3. So this is going to be 4, 3. Let's do the same thing for V2. Let's see, to get up to V2, we would have to, well, we'd need to extend all the way up to there. So for 5, 5, all we need is, let's see, 5 of those purple guys and none of the blues. So V2, its coordinates with respect to T will be, let's see, 5 of the first and 0 of the second. And then for V1, let's see, V1 is over here it's over here. So to get it, I'll leave that first one there. To get it, what we'd have to do would be go down here, and down here, and then up. 1, 2, 3, 4, 5, 6. Now those are pointing in the opposite directions of the original ones. So what we'd have here for V1 is the purple. We've got -2 of those because they're pointing in the opposite direction. And then how many of the blues do we have? 1, 2, 3, 4, 5, 6. But again, they're pointing in the opposite direction, so -2, -6. All right, so let's go down and look at coordinate representation. So coordinate representation relative to a basis says let B be an ordered basis for vector space, and let X be a vector in there such that X is this linear combination with these coefficients. Then these coefficients here are the coordinates of X, of that vector X with relative to the basis B. And we write the coordinate vector out like this. So it's exactly what we did in the previous problem. We typically write this out as a column vector. Okay, let's do there's a couple of examples here I want to look at. This first one says find the coordinate vector of this with respect to the standard basis. Okay, this is actually kind of a silly question. It's saying find this with respect to the standard basis. Well, it's the standard basis, so what we've got here is X. It's going to be 12, 10, negative 7. Because it's, 12 times this guy plus 10 times this guy minus 7 times that guy to get our coordinate vector. And I guess I need to be careful here. Notationally, I should put a bracket around this, and then there's a subscript here with the basis name. So X sub S is just 12, 10, negative 7. All right. Now let's find 12, 10, negative 7 with respect to this ordered basis. Okay, this one we've actually got to do a little bit of work for. And I'm going to write this one out long because it's the first one. But what you would do here is you would say C1 times 117 plus C2 times 201 plus C3 times 559 equals 12, 10, negative 7. And you could write it like this, or you could write it, each one of these as a column vector. So we're just trying to figure out what the coordinates are that give us 12, 10, negative 7. And of course, the way you solve this is by putting it into an augmented matrix and row reducing it. So you get 117, 201, 559, and then 12, 10, negative 7. Now, we're going to row reduce this. Before we do it, though, let's think about something. These three vectors here form a basis. That means they're linearly independent. When we row reduce this, we already know what the answer is going to be, at least on this side of the augment line. We know it's going to row reduce to this because those three things are linearly independent. It's the other three numbers that we need. So let's get Octave to do that for us right quick. All right, so my matrix here is 1, 2, 5, 12, 1, 0, 5, 10, 7, 1, 9, negative 7. We'll reduce that, and we get this, negative 5, 1, 3. And that's my coordinate vector. So let's see, what was this? It was called X. So X with respect to this vector was called B is negative 5, 1, 3. All right. 103, the coordinate vector X in R2 relative to this ordered basis is this. Find the coordinate vector with respect to the standard basis, or in other words, the normal coordinates. Okay, notice this is the opposite type question. Instead of telling us to find the coordinate vector, it's giving us the coordinate vector. So this is the set of coefficients that go with that. So that would tell us that X is 5 times 3, 3, plus 3 times 0, 2. So that's 15, 15, plus 0, 6. So X is the point 15, 21. All right, find the coordinate vector of x equals 12, 11, 19, 26 with respect to this ordered basis. Tell you what, let's put the rest of these examples in the next video.